All right, we've had our fun, so let's go ahead and implement a generative adversarial network using a notebook here and actually see how they're running under the hood here and how to actually code one up. A surprisingly small amount of code here, so not a whole lot to go through really. They're deceivingly simple, although they're very complex to train. Now again, these are very computationally intensive things to train, so if you don't have a GPU, you probably don't want to be doing this yourself. Let's go ahead and check if we have one with this first block of code, and that will go off and load up TensorFlow, which will take a little bit, but we can see that I do have one GPU available for training. If yours says 0 and you do have an NVIDIA GPU, again, head over to this link and it will talk to you about how to install TensorFlow GPU under Anaconda. Just pip install TensorFlow-GPU, but first you'll probably have to need to install some dependencies like the CUDNN library, which requires going to the NVIDIA developer website, signing up for an account there and all that stuff. But it is worth it for accelerating this training. All right, as before with the VAE sample, we're going to load up the fashion MNIST dataset, and we're going to be creating a GAN that can generate random articles of clothing. So let's go ahead and load that up from the keras.datasets package. And as before, we're going to merge together the training and testing datasets just to get more training data. Again, our goal here is not to classify data, it's to generate fake data. So there's really no use for the test dataset here. We're just going to glom it all together. And while we're at it, we'll normalize that image data from character values from 0 to 255 to floating point values between 0 and 1, because that's what sigmoid functions expect. And we will reshape the data, adding that extra dimension that we need for the CNN layers, for the convolutional layers. We'll also shuffle it and batch it up while we're at it in a batch size of 64. Oh, there's our first hyperparameter that we might want to tweak. Not much going on there. All right. So let's start by setting up our generator model. Again, this is the thing that's trying to generate fake images just given a random input. So it makes random pictures of, well, articles of clothing in our example here. All right, let's walk through what's happening here. We import the stuff we need from TensorFlow and Keras. Another hyperparameter here, how many dimensions of noise do we have? How many inputs do we have going into this thing? So we're going to start with 150 random noise values here. And we'll use that as our input. Again, you can change that and see what impact it has later on. Let's set up a sequential model in Keras, starting off with that noise vector there of 150 noise values. And we can play with what kind of distribution that noise is as well. We'll feed that into a dense layer of 7 by 7 by 256. And we'll do a transpose convolution on that in 3 layers, working up to a final image when we're done to reconstruct that. So again, this is very similar to the decoder from a VAE, right? Pretty much the same thing. So you can see how these things are very closely related. We'll print out a summary of the model just to make sure it looks right before we move on. Yep, looks sane to me. Next, we'll make our discriminator model. And again, this looks a lot like the encoder from the VAE, right? So what we're taking here as input is a 28 by 28 by 1 image, 28 by 28 pixels, 1 channel of color, grayscale. Feed that into a 256 element convolutional 2D layer, then to 128, and we'll flatten that down to a dense layer of just 64 neurons, and we'll apply a dropout phase to that to prevent overfitting, and finally output a final number of yes or no. Does this thing think that it's actually real or fake? So that's the main difference there from VAEs. You know, we're not actually trying to generate a vector of latent features here. We're just generating an output of, do I think this is a real image or do I think this is a fake image? But otherwise, pretty similar to the encoder from a VAE. Let's go ahead and hit that. Model looks correct to me. One other thing I forgot to point out, we're using the ReLU activation function here on the discriminator and the leaky ReLU activation function on the generator. And that's just something that people have learned over time that works well. Just, you know, standard best practice there. All right, let's set up our optimizers and loss functions here. So yay, more hyperparameters. So again, we have a optimizer for the generator and for the discriminator. We're calling that optimizer G and optimizer D. Both are going to be using the atom optimizer, but with different learning rates. And these are critical to get right if you want to have a stable model while you're training. If you get those wrong, it's just going to blow up. Kind of like we saw during that earlier demo of trying to learn that ring shape, if you remember back in the GAN playground. Our classifier for the loss function is pretty straightforward, though. We're just trying to figure out if things are real or fake. So binary cross entropy fits the bill for that. Similarly for accuracy, we want to see how accurate we are at guessing yes or no, is this a real image? So binary accuracy is totally reasonable for that as well. Shift Enter, we got that all set up. All right, let's tie it all together. So we'll start by defining our training for the discriminator. All right, so the batch coming in, we're going to read the shape of the data to figure out what the dimensionality of that is, what the batch size is, and then we'll create a vector of random noise that matches that batch size for the noise vector here. And we're using random.normal here for a normal distribution. Doesn't necessarily have to be a normal distribution. You could try a uniform distribution here if you wanted to as well and see what that does if you have time to play around with it. And what we're going to do next is concatenate the real and fake labels. So as we're going to see, we're going to actually stick the real and the fake data together as we feed it into the discriminator. And so we're going to have all the real data with a label of 1, followed by all the fake data with a label of 0 as we go in and define our labels here for the data that we're feeding in. That's what's going on there. We set up our gradient tape for training here. We first generate our fake data by calling the generator with that noise vector to get a set of fake images. We then concatenate that with the real data together. So we have the real data followed by the fake data. And again, that lines up with these labels of real and fake that we set up above here under y_true. We then feed that into the discriminator to see how well it does at guessing whether these are real or fake images, and then calculate the loss function that we defined above as to whether or not it got it right. All right, we have to also define the backward path for training here. We're just setting up, again, a gradient tape here, optimizer D that we set up before, apply gradients. Nothing really interesting here. It's kind of boilerplate code here, but we do pass in that discriminator loss function that we defined earlier. All right, we report the accuracy back here and keep track of that, print it out over time, and that's all there is to the discriminator model. Let's Shift Enter to set that up. And now let's turn our attention to the generator. So the generator's job is to not get caught by the discriminator, right? So we're going to say, we want to test how well you are at guessing that it was real. So as we go into our discriminator, we're measuring our success at whether or not it guessed that it was a real image, even though that it's fake. So that's what's at the heart of this training for the generator that's going on here. Again, we extract the batch size from the shape of the input data. We set up a noise vector that matches that batch size. And we just set up a vector of 1s because we're measuring how well we are doing at being classified as real. That's what 1 represents. So we set up our gradient tape here, and this is kind of the heart of it all here. We take that noise that we generated, pass it into the generator to create a bunch of fake images for whatever the batch size is. We take those fake images and then pass them into the discriminator. And we get back from that whether the discriminator thought those different images were real or fake. We then calculate our loss based on how well we did at making the discriminator think that our fake images were actually real ones. All right, so that's what's happening here. Not too much code really. The rest is kind of boilerplate again. We're tying together our back propagation and keeping track of the loss and accuracy over time. So Shift Enter to set that up. All right, a little handy dandy function here to visualize the generated images as we're going. So all this is going to do is take as an input a model. It's going to pick 81 random numbers here and pass that into whatever that model is, some sort of a generator, and visualize what it came out with in a 9x9 grid. So just a little helper function to visualize 81 random images given some model. And now let's actually do the training. So we aren't going to just use a one-line fit method here to do that. The reason is the original GAN paper actually would run multiple discriminator training steps for each generator step. But in our case here, we're going to keep it simple and just do, one discriminator training step followed by one generator training step. But if you wanted to, you could actually duplicate this discriminator training multiple times to more match what the original paper did. So it gives you some flexibility and things to experiment with again. Fundamentally, though, all we're going to do is go through 30 epochs. We're going to train the discriminator, keep track of the overall loss and accuracy, train the generator, again, keep track of our overall loss and accuracy, and just print the performance as we go. Also, for every other epoch, we're going to call that plot images helper function again to visualize 81 random sample images from our generator model. So at every second epoch, we're going to take our currently trained generator model and all the weights that it's learned so far and just visualize how good it's doing at generating fake images of clothes. So let's go ahead and set that up. And this is where the training starts. This is going to take a while, guys, but let's at least see if it kicks off successfully. Even with the GPU, this is going to be an incredibly intensive operation. All right, here we go. So here we are at epoch 0, kind of getting random blobs here at this point, as would be expected. But let's wait for at least the next visualization here at epoch 2. Again, what's going on here is our generator is learning how to trick the discriminator. And the discriminator is trying to learn how to discriminate real from fake images at the same time. It's adversarial because these two things are in tension with each other. And getting that balance just right is the key to creating a generator that can create convincing fakes. All right, epoch 2 finally came back, and well, still not really recognizable, but you can see that we're getting somewhat more complex shapes out of it already. We're going to go ahead and let this run for 30 epochs and see what we end up with. It's going to take a while, so I'm just going to pause the video here and come back when it's done while my GPU heats my room. All right, about half an hour has passed here, and my GPU has been working overtime here. It's actually hot in the office now here, so the other sort of dirty secret of deep learning is how much energy it consumes. Definitely something to be aware of and cognizant of. Let's see what happened, though. So as you can see, in epoch 0, just getting some random blobs. Epoch 2, not so much better. And by epoch 4, it's starting to do some more complicated stuff here. And starting to form into something sort of recognizable by epoch 8. These are starting to look like shirts and pants, I think. And by the time we get to 10, they're definitely starting to become recognizable. And over time, it just gets better and better and better. So even though we stopped it at 30 epochs, because, you know, I just don't want to destroy the planet by running it further, you can see the trend here that it is, in fact, getting better and better over time. And by the time we got to 30, well, we actually stopped printing it out at 28 here, just to a vagary of the code. But even at the 29th epoch, which is really 30 because we started counting at 0, the discriminator was still only 80% effective at discriminating real from fake. So there was still room for improvement here. We could let this train even longer to get even better results if we wanted to. Very intensive to train these things. And again, they're very touchy. So, you know, given that you have to really run these things repeatedly to tune all those hyperparameters, you can see how training a GAN can be a very time-consuming and energy-consuming proposition. But these are reasonable results. You know, these definitely look like dresses and shirts. Well, it's mostly dresses and shirts, isn't it? We'll talk about that in a moment. Let's just take the final train model and, again, just spit out 9x9 random images here to see what our final results are. And kind of points out in the comments here that it's kind of noteworthy how quickly it can generate those images once you have the trained model. So there's actually a demo on the NVIDIA website where they created a GAN that recreates a game of Pac-Man just based on analyzing the video of people playing it over and over and over again. So it can really, you know, represent anything you want without any real knowledge of what's going on necessarily. Anyways, you can see here, these look like reasonable dresses and sweaters, I guess, but that's it. So we're seeing that mode collapse problem that we talked about before, where we're really just measuring its ability to generate pictures of clothing. And we're not measuring its ability to generate specific types of clothing, just whether or not that generator can generate an image that can fool the discriminator into thinking that it's real. So it kind of found a way to cheat here because, you know, different types of shoes are going to be more complicated than generating a picture of a pair of pants or a shirt. And given the limited training time that we had, that's kind of what it converged on. So that's the mode collapse problem that we discussed earlier in the slides. But overall, pretty satisfying results given just 30 epochs and a pretty simple training data set there. Obviously, you can tell that there's a lot more to explore here. There's quite a gap between these results and all those face swapping apps that you see on your phone, right? So obviously there's much larger GANs out there that train for a much longer period of time that are able to generate those convincing fakes of real pictures of human faces, which is really the hardest thing to get right. But it's out there. And this is just the tip of the iceberg as far as GAN research goes. This really is sort of the cutting edge of deep learning research these days. If you look up GAN model zoos, you'll see that there's a huge variety of different models out there that you can work off of and build off of for very specific problems. And people incorporating GANs into larger systems. You know, for example, there's something out there that will automatically generate a talking head given a picture of somebody. It can like look around, its eyes can move around, it can fake talking to you and everything by sort of melding together the feature extraction of somebody's face with GANs that can create patches of that face that do different things. So lots of exciting innovation going on in this space right now. Again, I'll remind you from the ethics standpoint, please use this technology for good, and please be cognizant of the energy that it requires for training. So that's GANs, an introduction at least, enough for you to go off and learn more and be a little bit dangerous with it.